Good day and welcome to this lecture. In this lecture, we will be treating gas absorption modeling, right? So now, gas absorption is a technique that is used to separate unwanted components from a mixture of gases, right? So if you have a mixture of several gases and you want to separate certain unwanted gases from that mixture, then you may want to use the gas absorption process, right? So the feed to the process is usually a mixture of gases. Then you have an absorbent that is expected to make contact with the mixture and then absorb those unwanted gases. And most of the time the absorbent is usually in liquid form, right? So that's it. So it's just a technique used in separating gases, right? So now this gas absorption modeling has three main stages, right? Has three main stages. You have the absorption of unwanted gases, right? The separation, that's where the separation takes place. That's the first stage. Then you have the regeneration of the absorbent, right? The regeneration of the absorbent, and then the recycle of the absorbent back to the absorption tower or the absorber, right? So you have these three main phases or stages: the absorption, the regeneration, and then the recycle, right? So now you have certain absorbents that can be used for this absorption, and then we have some popular ones listed here. You have the MEA, that is the monoethanol amine, the DEA, the TEA, the MDEA, and then there are lots more. There are a lot of them. There are a lot of absorbents, liquid absorbents that can be used for gas absorption, right? Depending on your preference. Now, in fact, some of these absorbents can actually be mixed, right? You can mix two or more of these absorbents to create the absorbent for your process, depending on what you are looking out for, right? So that's it. Now, to illustrate what I'm talking about, so this is a simple gas absorption process, right? This is a simple gas absorption process. So the first stage, as I said, is the absorption of the unwanted gases. Now that takes place in this particular column here, right? This first column. Then you have the regeneration. The regeneration takes place here in this distillation column, and then you have the recycle. You have the recycle of the absorbent back to the absorber, right? So those are the three main stages. You can still have minor processes in between, but those are the three main stages of this particular process, right? So you have your absorption, your regeneration, and then your recycle, right? So that's it. So this is what we'll be modeling, right? This is what we'll be modeling, just for you to understand how this absorption simulation works, right? So this is what we'll be modeling, right? So now for gas absorption is a special kind of simulation, right? So most of the time, most property packages will not even work for it, right? They are not ideal for gas absorption, right? The major property packages that work for gas absorption are the acid gas property packages, right? They were specifically designed for gas absorption, right? So they were specifically designed for gas absorption, right? So any of the acid gas property packages can work for this particular process, right? So in this case, we are going to be removing CO2 and H2S from our feed stream, right? So we have a feed stream with this composition here, right? So we are going to be removing CO2 and H2S using this gas absorption process, right? Someone asked a question on it, so I'm using this particular tutorial to answer that question. So we are in our feed stream, we have CO2 and H2S present, and we are going to use this particular model to remove CO2 or separate it from our mixture, our gas mixture, right? So let's begin the simulation. You go to the simulation environment, then you add your components. From the components we have here, we have nitrogen, CO2, H2S. So these are our components. All our components have been added from the component list. Now, in this particular gas absorption, right, in your component list, you must have an absorbent, right? You must have an absorbent in your component list. In this case, I will be making use of DEA, which is diethanolamine, right? DEA. You can use any of the other ones or a combination of more than one of them, right? So, but in this case, I want to use diethanolamine, right? So you must have an absorbent in your component list, right? It's compulsory. Then for fluid package, you have to make use of acid gas, right, for your fluid package. So you click on it. In fact, it's Hysys automatically adds the fluid package for you, right? In this particular model, it doesn't happen in other simulations, but for this absorption simulations, it's going to automatically choose a fluid package for you. In this case, it chose acid gas chemical solvents, which is actually okay for this particular model, right? So when you are simulating this gas absorption, right, you must choose one of these acid gas fluid packages, one of the 4 of them, right? So we have specified our components and fluid package, right? We can now start the simulation. So you just go to the simulation environment. So we are in the simulation environment. We specify our feed stream, right? That's the first step. You bring out a material stream from your model palette, and then you specify it. So we have our feed, then feed properties. You have pressure, seeing pressure of 200 kPa. Then temperature is room temperature. Then molar flow is 572. Yes, 572. Right, then composition, we have the composition there. We need to specify this composition. So we go back to the model, you double click on this, then you type in the compositions of each of them, right? So after adding the component, I see that I have a total of 0.9997, right? I want to add 2 more components to the component list, so I'll quickly do that. Back, just add 2 more components and we are good. So N-hexane and then N-heptane, right? Then we can go back to the simulation environment. Nope. Yes. So I will specify the composition again. So from here we have 5 minus 4. So once you are done entering in all the values for mole fraction, you should have something like this. Then click OK. The feed stream is fully specified. We can now start the modeling properly, right? So we are going to be heating this feed or pressurizing it first before we now heat. First off, we need a pump, a compressor, right? In this case it's a gas mixture, so we need a compressor to increase the pressure of our feed. So we get that from here, right? Then let's check our compressor details from this. So the outlet pressure of the first compressor is 7006 kPa. That is what we'll be specifying here. So our inlet is feed, then our outlet is cooler feed. Outlet is cooler feed. Then energy is feed Q, right? So we have specified the outlet pressure, the outlet stream, and then the energy stream. So we now need to specify the outlet pressure, which is 7006 kPa, right? So we have been able to increase the pressure of the feed. The next procedure is to cool the feed before it is sent into the absorber where the absorption is going to take place. So the next step is to get a cooler that cools the feed, right? So outlet of this is sour gas, then this is cooler feed, the inlet, then this guy can be Q1. Then we check for the specification of the cooler from our problem statement. Let's see the cooler. The first cooler is outlet temperature is 32 degrees Celsius, and then outlet pressure is 6996, right? So let's go back now. From here, as we increase the pressure, you will notice that the temperature also increased, so we have to cool it back, right, to reduce the temperature. So that's why we need a cooler here, right? The increase in pressure increased the temperature from 25 to 384 degrees Celsius. So this, we have 32 here, then we have 6996, right? 6996 kPa for the pressure. So the pressure drop is automatically calculated. So we have specified this, right? Now we can now send this into the absorber for the absorption to take place, but before then we need to create a feed stream for our absorbent, which is DEA. So we are creating a feed stream for that, right? Both of them will be sent as feeds into the absorber. So this is the feed stream for DEA, which is our absorbent. The DEA has its own properties as well. Okay, DEA, you have this, you have pressure is 6996, pressure is 6996, then molar flow is what? Molar flow is 995.9. Then the temperature is 40 degrees Celsius. Then the composition, so we specify composition so that it can be fully specified. You have 0.0017 for CO2, 0.0017 for CO2. Then we have some amount of water. H2O is 0.7821. 0.7821. Then DEA is 0.2162. 0.2162. Then you click OK. So this is fully specified. So at this point, both the DEA and the feed can now get into the absorber, right? The absorption column, right? So in this we have our specification for CO2 and H2S. So these two will be separated from the other components of the gas mixture via the absorber. So we get the absorber from the model palette, right? This is an absorber here, so we are using it for this particular phase of the simulation, right? I can reduce this. Yes, what else? Auto hide. Okay, so this is better. So we specify our absorber, we specify the inlet, the outlet, right? The top stage inlet is the absorbent, right? The top stage inlet is the absorbent. Then the bottom stage inlet is the feed, the gas feed. Then we specify our outlet, right? Our outlet top is sweet gas, then bottom is a mixture of the unwanted gas and our absorbent. We'll name it as rich DEA, right? Then number of stages is 10. Let me check the absorber specifications. Yes, number of stages is 10. So we can continue. So we have specified this first stage, right? So you click on next. Now the top stage pressure and the bottom stage pressure are the same, 6996 kPa. Then you click on next. Then we will not specify the temperatures because we don't have those values. They will be calculated by Hysys. Then you click done. Then we can specify any other. Okay, those are all the specs we have for this absorber. So since we don't have any more specs, you can run the column to see if it converges. Okay, so the column has converged, right? The column has converged. So we have modeled the absorber column. It's actually a simple column to model, right? It's not really so rigorous like that. It's a simple column to model, especially when you don't have so much specs. Now let's check the worksheet and then the composition. So from here you would see these are the inlet streams, DEA and sour gas, right? Then the outlet streams are sweet gas and rich DEA. The sweet gas is the top and the rich DEA is the bottom, right? From here you will see that the H2S and CO2 have been highly removed from the gaseous mixture, right? So H2S is removed completely while CO2 is just a very little amount of CO2 that is remaining in the gaseous mixture at the moment, right? While the CO2 and the H2S have been absorbed by the DEA, which is the absorbent. So both CO2 and H2S are in the DEA stream at the moment, which goes out from the bottom of the absorber, right? So that is how this gas absorption works, right? So when the absorbent makes contact with the gas mixture, it is able to remove the unwanted components from that particular gas mixture, right? So but this is just the beginning aspect of this particular model. This is the absorption of the unwanted components. We still have the regeneration of the absorbent and the recycling of the absorbent to model, right? So we still have to continue with the modeling. Now for the before we go into the regeneration, we will specify some equipment. So the next thing to specify is a valve for this bottom outlet. The bottom outlet would have a valve, right? The bottom outlet would have a valve. So the valve pressure drop is 6376. The pressure drop, so just specify this as V out. Then this is rich DEA. Then the pressure drop is 6376. Okay, 6376. That's okay. So we have specified the pressure drop, and that is fully specified. Next we are going to specify a two-phase separator, for this particular valve outlet. A two-phase separator here. So we have and then we have the liquid outlet, and this is fully specified. No additional specifications to be made to it. So this is the specification for the two-phase separator. No additional data for it, right? So it's fully specified. So the next step is to model a heat exchanger, right? A heat exchanger for the liquid outlet of the two-phase separator. Now the outlet of that heat exchanger is supposed to enter the distillation column. That is where the regeneration takes place, right? So when we model a heat exchanger here, that heat exchanger now feeds the distillation column, right? And then the absorbent is now separated from the unwanted gases, right? While the absorbent is then recycled back into the absorber. So we are going to be modeling a heat exchanger right here. just here at this portion. So you get a shell and tube heat exchanger. That is what we are using for our process. Now we have our specifications for the shell and tube. So this guy, nope, that's wrong. It's the liquid outlet that goes into the shell and tube, right? Then we have our outlet for the tube, which is rich feed, right? Then okay, we can specify this. Then our shell outlet, this is our shell outlet, right? So we will get our other specifications from the question. This is E100. Okay, so this is the specification for the heat exchanger. The specification for the heat exchanger, the model is simple endpoint. Then the pressure drop model is simple endpoint. The pressure drop is 70 kPa for both the shell and the tube side, right? Then back to this, we may need to specify the tube outlet temperature. Let's see, the tube outlet temperature is 60 degrees, right? 60 degrees. Yeah, so the tube outlet has solved, right? Now these other streams, the shell inlet and the shell outlet, are not going to solve. They are not going to solve until we simulate the distillation column and then simulate the recycle of that distillation column product, right? That is when they would solve. So we'll be treating that in the next video tutorial, right? I don't want this video to be too long, so I just wanted to introduce the gas absorption to you guys, right? So we'll continue this particular model in a subsequent video, right? So if you have questions on what has been taught today in this video, kindly drop your comments, then like this video, share with your friends, and also subscribe to this channel for more tutorials on process simulation. Thank you for joining me. Do have a good day.